Hello everyone. Thank you for giving me the opportunity of being with you today. My name is Jose Cafiero. I'm from Argentina. I hold a degree in economics from the University of Buenos Aires. I hold a master's degree in international affairs from Columbia University in New York. I used to teach microeconomics at the University of Buenos Aires. I used to teach regional economic integration at the University of Buenos Aires. I used to teach international trade at the University of Museo Social Argentino, and I used to teach econometrics at the University of La Matanza. Today, we are going to talk about units of measurements and functional forms. The first topic, units of measurements. What happened with the linear regression model when we change the units of measurements of the dependent or independent variable? Take a look at equation 1. If the response variable y sub I is, for example, multiplied or divided by a constant k, then the slope beta sub 1 and the intercept beta sub 1 have also to be multiplied or divided by the same constant. Why? Because we have to maintain equality in equation 1. We have to maintain the equilibrium in equation 1. And that's the only way. On the other hand, if the explanatory variable x sub I, or we are going to call also the independent variable x sub I, is multiplied or divided by the constant k, then only this slope beta sub 1 has to be divided or multiplied by the same constant. That is, we have to reverse the operation in order to maintain equality in equation 1. All in all, the goodness of fate, the R squared, doesn't change. Why? Because numerator and denominator of that expression are scaled by the same value, so it doesn't change. Now, second topic. The term linear regression denotes a model that is linear in the parameters but not in the variables. That means that we can use many functional forms depending on the problem we are analyzing. Remember first that we can present the linear regression model as we can see in equation 2. Y is an n by 1 vector containing the n observation of the response variable. X is an n by 2 matrix with the columns of ones and the other columns containing all the observations that we have of the explanatory variable. Beta is a 2 by 1 vector containing the coefficients to be estimated. And U is an n by 1 vector representing the error term. Now, vector U in equation 2 contains all unobserved random factors that affects Y. The first component of beta sub 0, indicates the hypothetical value of y sub I when x sub I equals 0. The second, as you may know, component of beta sub 1, indicate the expected impact of each y sub I of a unit change in x sub I, holding not only everything that constitutes u sub y constant, but also all unobserved random factors captured by u sub y have to be independent of x sub I. Otherwise, our estimate is going to be biased. Now, going to new functional forms that we can use. Suppose that our idea is to estimate the elasticity. That is, the percentage change in y sub I associated with 1% change in x sub I. In this case, we can adopt other functional forms. What we can do? Well, the best way is to take logs on both sides of equation 2, run a regression, and then our new beta sub 1 coefficient is going to represent the constant elasticity of the model. This is called the double log or log linear model, also known as a constant elasticity model. Again, the elasticity beta sub 1 is a constant. If we don't do the log transformation in equation 2 and just work with equation 2 or 1 as they are, then we are not going to have a constant value for elasticity. The value of elasticity is going to be beta sub 1 multiplied by x sub I divided by y sub I. And that is a value that is not going to be constant. So in order to have a constant elasticity value, we have to take logs on both sides of the equation. Other example. Sometimes we might be interested in finding the rate of growth of certain economic variables. Take a look at equation 3. Suppose that we want to estimate the rate of growth of the GDP of certain country during a certain period of time. We are going to have our y sub t, that is the GDP at time t, y sub 0, that represents GDP at time 0, and then we have our g value, that is our implicit rate of growth that we have to calculate. We can do simply solve in 3 for g, and we can have a value. But we have a much better way to have our g value, a much better informed way to have a g value. If we take logs on both sides of equation 3, then t, as you can see at the end of this slide, is going to be our explanatory variable if we run a regression of the log of y sub t over t. And then we can estimate g taking the antilog of expression beta sub 1, that is going to be log of 1 plus g, and subtract 1, and then we are going to get our g, that is our rate of growth. And this is much more informative than simply solving for 3. Why? Because we can run our hypothesis test, testing if g is significantly different from 0. We can assess through the R square how well this rate of growth fits to the real rate of growth that we are going to see during that period of time. Then also remember that d is a sequence of numbers, so the independent variable is going to be exogenous. We don't have the problem of bias estimator that we saw in the last session. And so in that way, we are going to have much more information about g. So I advise you, when you calculate the rate of growth, that you use this linear model in order to estimate g. Other example. We can have certain problems that needs to be worked out with what is called the reciprocal model. The reciprocal model is the one that I just put in equation 4. This model, as you can see, is not linear in the explanatory variables, but linear in the parameters. So OLS applies. The main characteristic that you can see in equation 4 is that as x sub I increases, the value of 1 over x sub I comes close to 0. And then y sub I approach beta sub 0, then in the case is going to be a limit value. And there are two important models in economics. One application of equation 4 of last slide has been the Phillips curve that connects inflation or wage inflation with the unemployment rate. And there is some regulatory standards, some institutional standards in a society that precludes the rate of inflation or the wage inflation rate to become lower despite the increase in the unemployment rate. And this is something that we can measure through equation 4, through a model like equation 4. The other example has been the Engel curve that describes the relationship between consumption and income. And there is also a case of association point, saturation point, where despite the increase in income, consumption doesn't increase any longer. Why? Because as I told you, there is a cessation or saturation point that precludes that increase. That is everything that I have to say today. Thank you so much and see you in the next lecture. Hello everyone, this is Jose Cafiero again. Now we are going to do some practice using R. In order to do some exercises applying what we saw in the theoretical part of this lesson, we can use a database from the International Monetary Fund that is called the World Economic Outlook database. You can get that database in the address that I just wrote down in the second line of this slide, and you just download the World Economic Outlook database, and I strongly advise you to use the CSV extension in order to do that. Then enter R, just call the library tidyverse, and then you can download the database, just name the database, then just put the name that you want, use the read CSV command, and begin to prepare the data. The first thing that you have to do is to get rid of the columns or variables that we are not going to use. The second thing is transform the data that is in a wide format to a long format. It's better for do all the things that we are going to do. Then just check the type of all the variables in order to see if they are in the type that you want or you need in order to do the calculations. Do all the transformation that you need to do, as I just wrote down there, in order to get the data ready for using in order to do linear regression. Then I strongly advise you to set up an auxiliary data frame or table. I call it this because it includes all the description of all the variables that are in this enormous and important database. And this is something that is going to help you if you decide to do other work with this database, just do other estimations, whatever you want to do to use this database is going to be useful so you can find all the variables that you have at your disposal, etc., etc., etc. Well, for the first thing that we are going to do, suppose that we want to study the relationship between the gross domestic product of central countries and the balance in current account of those countries for a certain period of time. Then what we have to do is, with all the transformation that we just already have done, we select the variables, the way I just wrote down in the second bullet of this slide, and what we have to do immediately is to check if there are missing values in the data. If the missing values are not so many, we can get rid of missing values the way that I did there, because we don't have any missing values in this data, but you have to check for that, and get rid of the columns that we are not going to use any longer. Then, ironically, we again transform the data from the long format that we have now to a wide format, so we can easily select the variables that we are going to use. And we check again for missing values and select finally the data that we are going to use. The first things that we have to do is to do some exploratory data analysis. And this is very simple for us in this case because we have only two variables. Yes, you can use, as I did, ggplot. And just take a look at what is telling us this data. And the first graph that I just put for you there is a scatter plot of the data and GDP in the x-axis and BCA in the y-axis, and all the scatter plots that tell us how the data is distributed between these two variables. And then we did a simple thing with ggplot with the color geom smooth. We can do locally estimate scatter plot smoothing. That is the curve line that you see in blue, and it's a kind of local mean regressions of each of the points, and you connect off all these mean regressions and you are going to get that curve in blue that you see in the graph. And this is very instructive. This is very descriptive because it's just telling us that at the very beginning we see a positive relationship between NGDPD and BCA, but it's not a linear relationship. Indeed, it's more or less curve shape. So then we are going to compare this when we get to the linear regression and try to see the difference. Then we run the linear regression model. We just name the model. In this case, I name it wall and call lm. That is the command that you use in R in order to do a linear regression. Just call the dependent variable BCA. Just call the independent variable NGDPD. That is the GDP. And just call the data. Then call another library sgplot in order to present the results in a more clear way. And we have the first estimate here in this table. And you can see that the value of the slope coefficient indicates that the billion US dollar increase in NGDPD is associated with a rise in BCA of 0.03 billion US dollars. As we saw in the theory part of this lesson, if and when all the random variables in the error term are not associated with NGDPD, this estimator is unbiased. Otherwise, it's biased, and we have to correct that problem. We can take a look at the p-values. That p-values tell us that we can reject the null hypothesis that the estimate from NGDPD comes from a t-distribution with mean equals 0. Thus, we reject the null hypothesis that the estimate is 0 with a 0.05 significant level and more reduced significant level attending to the value of the p-value is so low. We cannot do that for the intercept. There we cannot reject the null hypothesis that that value is different, statistical different from 0. And then we check the R square of the linear regression, and we can see that the R square is not so high, so we are not in a presence of a good fit. Indeed, we are in a presence of a very poor fit. We also have to check for the presence of heteroscedastic or autocorrelated error. We have to check how the errors behave in order to be sure that we have the best linear and biased estimator for that linear regression. So a whole battery of tests has to be done in order to be sure that we are in that kind of situation. Then we can do the analysis in order to assess the performance of the model, and we can think, okay, BCA surely depends on many other variables included in the error term. So there's a high probability that we are in the presence of a bias estimation. So, or we increase the quantity of the planetary variables, we can use instrumental variable methods, we can use two-stage least square estimator methods in order to overcome that problem. And we also have to correct heteroscedastic or autocorrelated errors in order to have, as I told you, the best linear unbiased estimator. When you correct, for example, for heteroscedastic error, the value of the coefficient doesn't change, but the standard error changes, and this is something that can change the p-value rejecting or not the null hypothesis that the coefficient is statistically significantly different from zero. As we saw in the last lesson, we can use many functional forms. Well, why don't we try to find out the elasticity? That is, what is the percentage change in the balance of current account associated with a 1% change in GDP. In that case, what we can do, as I told you, is transform the equation in logs, as I did there, and run again the model, and the results are here in this second table. And we can say that a 1% increase in NGDPD is associated with an increase in BCA of 0.88%. This is the value of the elasticity, and this is an inelastic relationship because the value is less than 1. If and when, again, all the random variables in the rotor are not associated with NGDPD, this is an unbiased estimation. We reject, in this case, the null hypothesis that the coefficients are statistical equals to 0, because the p-values allows us to reject the null hypothesis, and we can say that there is statistical significant different from 0. Also, you can take a look at the confidence interval values, and you can see that they don't contain 0 at all, so we are in the good way. Again, the R square has increased, but not to a quantity that pleases us. So again, we are not in presence of a very good fit. And again, check that the errors behave properly in order to go ahead with this linear regression, and otherwise you have to transform the standard error, you have to transform some of the variables. Again, check for the validity of the equation and the exogeneity of the independent variable. In this case, is this independent variable associated with variables that can be included in the error term. If we think that this can be the situation, you have to understand that you are in the presence of bias estimation, and you have to address that problem with incremental variables, increasing the quantity of variables using two-stage lists, where you have a lot of methods at your disposal in order to solve that problem. One thing that you can see is that the increase in the R square from the non-transform regression to the log transform regression can be appreciated in the distribution of the two variables. At your left, you have the distribution of the variables in their original form. At your right, you have the distribution of the variables in log forms, and this distribution is much more smooth, much more adapted at the distribution that we need in order to run linear regression. So this is something that you have to bear in mind when you work with the problem. Perhaps transform the variables in logs is going to be very helpful if you can do that and if you want to do that. Now just go to the growth equation, so to speak. The equation number 3 in the theoretical session. In order to that purpose, we take logs on both sides of the equation, the original equation, and our independent variable is going to be per for period, and we just run the regression, and we have got the estimates in the next table. As you can see, the final value for the rate of growth is going to be 4.66. And although this value is statistically significant different from zero, it's not precise enough. Take in account the L square. The L square is not so big in order to say that this is a very precise estimator. This is the beauty of using that kind of methodology in order to estimate growth rate. You can assess the quality of the value that you have at hand. Remember that per is an exceptional variable because it is simply a sequence of numbers. So we don't have the problem here of bias estimation. We have to check for the good behavior of the errors again, as you always have to do. And you can see in the next graph where I just put together the lowest regression estimator and the linear regression estimator, that the lowest estimator has a very much better fit than the linear regression estimator, but in this case we don't have a value. In the linear regression we have the slope, that is the value that we assign to the growth rate. In the case of the lowest estimator, we have different values depending on the year that we are analyzing or taking data from. Finally, we can assess the so-called Philip curve. Just go back to equation 4 from last lecture. Check the DEX table in order to get the names and the description and the units of measurements of the variables in order to be sure that what you are doing. Select the variables, check for missing value, get rid of the values that you are not going to use, select a period, and then you are ready to run a regression. And I just put you the first thing that we have to do, that is do some exploratory data analysis. And we are just familiar with our lowest regression, our linear regression, and we can see at the very beginning of this doing this linear regression that things are not the way that we think they were. So we can see that the relations is the opposite that the one the model prescribed, and the points do not fit so tight. Neither the lowest curve that is in green, nor the line in blue that is going to be the result of our linear regression model. Run the linear regression. See how you have to use the I expression in order to work with transform data in linear regression model in R. And the results are here. We can see that in this case, we can reject the null hypothesis that both coefficients are statistically different from zero at the 0.05 significance level, but the R square is horrible. So this regression is so bad that we need to change many things in order to improve these measurements. What we can do, we can change the model, change the shape of the model. You can add other variables. You can try to use logs, for example, in order to see if you can improve the fit of the model. But many things has to be done in order to improve this linear regression model that don't give us the results that we are looking for. Moreover, the sinus slope is practically the contrary that the one that the model presumes that we suppose we're going to get. If you get a better model, don't forget to check for the behavior of the errors, and don't forget to check to analyze if you can have the problem of endogenous regressions. So there is a relationship between the independent variables and the variables that are part of the error of the model. In that case, you have to use instrumental variables to stage square or keeping going to add variables to the model. Well, that is all that I have to say. I want to thank you you all for being with me today.